Hello, everybody. Now I'm gonna tell you of another uh, example that is related to the example of nonlinear system that you find in another video. In fact, is a bit this example is more articulated, is a bit more complex because it's called Newton solver. So the idea is to find the zero of a system of equations. So you have a system of equations, possibly nonlinear system of equations, and you want to find a zero. You know the Newton method is indeed one of the technique to find a zero, but this Newton solver is not a very appropriate name because, as we will see in a while, I'm not implementing just Newton. I'm implementing different methods, also methods that do not require the explicit computation of the gradient or the Jacobian. Okay, but let's do one thing at a time. Okay, the two main header files. Well, actually, the first header file one has to look is Newton traits. Again, I use the trait techniques to be able to change the types. And here, in fact, I only have one trait, okay? Which means that at the moment, I don't have many choices. It's a bit too complicated making different situations. So at the moment, I have only one trait. So here the traits are not used differently from the example of non-linear to be able to change different ways of representing the system of equations. Here, the traits have just the role to gather in a single place the main types used in the program. So that if in the future I want to change something, at least for what concerns the types, I just have to change in one single place. In particular, here I'm using always the eigen libraries because I'm using vector and matrices of the eigen libraries because I need to do operation on vectors and matrices. I need to solve a linear system because remember Newton requires solving a linear system with the Jacobian. And so, well, if you don't remember how Newton works for system, I'm not going to repeat it here. And get a good book of basic numerical methods, or look at Wikipedia and you find everything there. Okay. Anyway, so the argument is a vector of the eigen. A vector of the eigen. Here you can use vector, vector xd, but here just I put the full name. So it's an eigen matrix of doubles because we're working only with doubles here. The first dimension is dynamic, that is not determined at compile time. The second dimension is 1. That means that this is a column vector, okay? An arbitrary number of rows, one column. The return type is equal to the argument type because if I want to solve the system, I need to have the same number of equation as number of arguments. The nonlinear system type, again, a function wrapper, okay, is a function that takes an argument type, that is a vector of the eigen, and returns a vector of the eigen. How do I write it, this nonlinear system? It doesn't matter. Maybe I want to use the nonlinear technique I've explained in another video, or I can do whatever I want. Okay, the important thing that I need to have something that takes a vector of the eigen and returns a vector of the eigen. It's up to me. It's a callable object. Is an arbitrary callable object. It's a generic callable object. I can I can use whatever I want. Then Newton needs a Jacobian, and the Jacobian will be a matrix XD. That means a dynamic eigenmatrix of doubles. And the Jacobian is a function, however, and again, I'll use a function wrapper to wrap the Jacobian. The Jacobian is a function that takes an argument type and returns a matrix. That is evaluation of the Jacobian of the function at that point. Let's look at Newton. Newton takes a Jacobian. Now we are going to look at the Jacobian later on, and some options, Newton options. Now the Jacobian at the moment, let's forget about it. We're going to look at it later on. Let's take the Jacobian just something that takes, as we've seen, takes a point and returns a matrix. What are the Newton options? Newton options are just a set of options for my Newton, all put in a little aggregate. And this aggregate, of course, has defaults. So here, this is a nice trick. I'm saying that Newton options, I can give some options with this constructor, but by default, opt is just an instance of Newton options. This is just the default constructor of Newton options. And what Newton options are, well, we're going to see it. It's here in Newton method support. And Newton options is just a structure that contains a lot of things. In particular, contains a tolerance. The iteration stops when the difference between two successive iterates is less than tolerance. But I can also specify a tolerance on the residual, and the iteration will stop if the tolerance on the residual is satisfied. I can specify the maximum number of iterations. I can specify if I want backtracking. Backtracking is a special technique to make Newton more robust. Okay, because you may want to use it or not. I'm not going to explain here the detail of backtracking. Maybe I'm going to write a text file. I will add to this example a PDF file, a text file that you can compile where I describe the technique. Okay, but for the moment, it's not so important. With all this part is relates to backtracking. So let's forget at the moment. We put backtracking per false, so we don't have backtracking. We have also another aggregate that is what the Newton returns, because I want not just to return the solution, which is of course what I want, the zero, but also to return some other information. In particular, I want to know if Newton has converged or not. So I created with this structure, this little aggregate, where I have the solution, that is just a vector, an eigenvector of values, but also the residual, the rough residual computed, the last step length used, the number of iterations, if it has converged, and if it is stagnated. Stagnated means that it has not converged because the iterates are practically the same, so the method doesn't move, but the residual is still too high. So stagnation is just a type of non-convergence, because there are two ways Newton can not converge. One, if it is jumps between different values, so it doesn't stop, it just goes random, well, not randomly, but it just goes between different values, jumps from one to another, or explodes, gets, but very typically it stagnates. Okay, so let's go to Newton. Okay, and let's see how Newton works. So these are the methods. The main, of course, the main method is you can get the option, you can change the nonlinear system. These are just what is the most important one is solve. Okay, that's the main method. Takes an initial guess. You know that you have to start from an initial guess and return a Newton result. That is the structure that you have just seen. I may want to inherit from Newton, and so I have a virtual structure that has been set to the default. And we're going to see, I have this strange function here in the protected section that is used, and this strange structure, we will see, this is a trick, okay? I want my Newton method to not be too much verbose, but I want to give the possibility to the user to do something, for instance, print on the screen at every iteration some additional information. And to do that, I'll use this technique that is called the callback technique. It's used in many software. Okay, what's the idea? I keep somewhere. I decided to keep it in an internal structure, but it's not so important. I keep somewhere some information about the iteration. For instance, the current solution, the current iteration, the current residual norm, the current step length. I give some initial values, but it's not so important. This is something that this is structure, and then I have here it is. I have a member of this type, and here in the iteration we are going to see I will store some information during the iteration. Why I do that? Because I can, here I have this function callback. As you see, this function callback does nothing. This function callback has got nothing here. It's a no operation. This is what normally is called a no operation, not. Does nothing. So probably the compiler will just optimize it away. It does nothing. But it is virtual. So its reason of existence is to be overridden if instead I want this callback to do something else. So I give the user the possibility of inheriting from Newton solver to change this callback to do something, and we will see. And indeed, I show here already an example. Well, this callback, I need to add one last thing. This callback is called at every iteration. So at every iteration of my Newton, I call callback. By default, this callback does nothing, so probably the compiler has optimized it away. So the cost is zero normally of calling this callback. But if instead of Newton, I use a Newton verbose that inherits from Newton, it inherits all constructors, so it can be constructed, Newton verbose can be constructed as a Newton. The only thing that it does is that it overrides callback. And indeed, in Newton.cpp, we have solve, but we have also the overridden callback. And this overridden callback just prints on the standard output some information contained in the state of this object. Okay? So the current iteration, the current residual norm, the current step length, and so I can see this is done for debugging. Okay? Newton iteration is not converging. Why is not converging? Well, let's have a look. Let's use Newton verbose instead of Newton, so that at every iteration I have a few some information printed on the screen, and maybe I can understand better what's going on. Okay? The main method, of course, is solve. And this method is a bit, I'm sorry, I cannot explain it in detail because it is a bit sophisticated. Okay, I'll just give you some indication of the technique that I'm using. This is just a trick that can be replaced now with structured bounding if you want, just because inside the code I don't want to every time I call options.tolerance, options.minres, options.maxiter, and so on. These in C++ is not needed. C++ spares you the need of indicating these with a little arrow if you want to get a member of the class. Here I'm just saying options.tolerance is a member of the class. So I can avoid this with this little arrow. I put it here only because it doesn't harm, first. Secondly, because in Eclipse, if I write this arrow, Eclipse will just give me all the possible choices, so it is easier. Okay, if I will, and probably also Lion does the same thing. I don't know if Lion is more sophisticated and does not require to write explicitly that you want a member of the class. Okay, but unfortunately Eclipse requires you to write this arrow, and then you have the list of options. But I repeat, in C++, it's not required to use this. Okay? When you want just recall a member of the class. Again, here I'm just for the same reason. I don't want every time to write state, current solution, state, current iteration. I just create an alias. These are aliases. Okay? Are aliases. These I can want to write on top, so they're references. These are not want to write them on top, so I just take as a const reference. I get a pointer, I get a Jacobian, and then I set a few variables, and here's the main iteration. Here I solve the Jacobian, so here I solve the problem. I compute the residual. I run the Jacobian. I want to solve. I will compute the Jacobian on the current solution, and I will solve the linear system Jacobian current the linear system with the right hand side is the residual, and the matrix is the Jacobian at the current solution. Once I compute the Jacobian, this is the delta, how I have to advance. I do the current step length. The current solution now is the previous solution minus lambda times delta. Okay. Here is just a matter of habit. You can define the residual with minus the current solution. So the residual here is just the nonlinear system on the current solution. In principle, in some books, you find the residual defined as minus the current solution, and so here you find a plus instead of a minus. Okay, it's just a matter of convention. So if we ignore backtracking, as at the moment I want to ignore backtracking, we have done everything. I have computed the new solution. I compute the new residual. I compute the norm of the residual using the method norm of the eigen. You see, it's very convenient with the eigen matrices or vector. If you want to compute the norm of a vector in eigen, you just use the method norm, and then I check if I am decreasing, if the current residual is decreasing. If it's not decreasing, For two, for two consecutive iterations, I'm stagnating. Okay. And then I check if I'm converging. I've converged if the current residual norm is less than the tolerance that I've given. Here I put an and. Sometimes you put an or. Here is very strong. Both conditions must be satisfied. Both the residual has to be below the tolerance, and the difference between two consecutive iterations must be less than tolerance as well. And you see, here I call callback. Normally callback does nothing. But if I use Newton verbose, callback will print on the screen a few information. And then I continue iterate. You see, here I have a while. This is a do while. Okay. Until I have converged, I will repeat. I have converged, or if I have exceeded the maximum number of iterations, or if I am I have a third condition, or if I have stagnation, if I am stagnating. If I'm not decreasing the residual for two successive iterations, I stop because there is no way I get better. And then I return Newton solution, the current solution, current residual norm, current step length, current iteration, if I'm converged, if I'm stagnating. That's it. Jacobian are not just Jacobians, because Jacobians have the most important method that Jacobian is this solve. Solve takes the point where I want to evaluate the Jacobian, and the right-hand side of the system, Jacobian y equal b. Okay? And returns, of course, the result. Returns the result of the solution of the linear system. So I'm not. This is the only thing that I need for the Jacobian. Okay, I have a method because I need to set the nonlinear system because the Jacobian should know the nonlinear system. So I have a pointer to the nonlinear system. Okay, the Jacobian, when I need inside my Newton method, I instantiate a Jacobian. So my Newton contains a Jacobian, and the Jacobian contains a pointer to the same nonlinear system used inside the Newton. This is done in the constructor of Newton, because in the constructor of Newton, I pass a Jacobian, I pass in fact a unique pointer to a Jacobian, and I set the Jacobian by passing the same nonlinear system that my Newton is using. Okay? So why do I need to know the nonlinear system? Because some Jacobian are built starting from the nonlinear system. I've implemented, this is a base class, I have derived a discrete Jacobian that is just a Jacobian computed by finite differences. Okay? I've implemented an identity Jacobian that just returns is just identity matrix. If I use an identity Jacobian, my Newton becomes a simple fixed point iteration, just a basic Richardson type of iteration. The full Jacobian, but in this case, I need to pass the function that implements the Jacobian, and I have to compute it myself. Okay? And I have some other Jacobians that are not Jacobians. I can say, after all, the Jacobian, I'm never computing the Jacobian. What I'm doing, I need to solve a non-linear system. Sorry, I need to solve a linear system whose matrix is just the Jacobian. But how this linear system is made, I don't care. Okay, and in particular, this allows me to implement quasi-Newton methods. A quasi-Newton method is Broiden, where Jacobian is not a Jacobian, but this solve will just solve the, the problem with an approximate Jacobian. Which approximate Jacobian? The approximate Jacobian given by the Broiden formula. Okay? If you don't remember the Broiden formula, go to Wikipedia, type Broiden method, and you get it. Okay? I have two different types of Broiden. I have the Eirola-Nevaligna method. These are all quasi-Newton methods. It is a method where the Jacobian is approximated. So here you don't only have the Jacobian, but you have the possibility of using approximated Jacobian. And you may, if you want to, you may add some more. Why not? Okay? Everything works? Yes, of course. All my code works. All my codes work. Where is the main? Main. Do you find the main here? Here you have some explanation of the Newton solver. So it's already present, an explanation of the Newton solver. And I don't find a main. It's just because I don't see it. Oh, here it is. Okay. The main, I just create my nonlinear function. Is a function 3 by 3. And the first equation is 3 times 0 minus cosinus of x1 times x2 minus 0.5, and so on. So here I'm defining. Here is a simple function of which I have an exact Jacobian. Okay, so this is just the Jacobian of this. Yeah. See? Very simple eventually. Very simple. Here I'm just specifying all the members of the matrix of the Jacobian. And here I just want to change the non-Newton options. So I create an object Newton option, and I change something. So these have got all the defaults, and then I change some of the defaults. For instance, I want the backtracking. I don't want to stop on stagnation. Why not? And then I want Newton verbose. So I want to have something on the screen. Create a Newton solver for my nonlinear function, my Jacobian. I pass the Newton options, and then I just run. I run my Newton solver, and I get the information. I remember that the information is in an aggregate. So if you want, it's not. I mean, it's not compulsory to use structural bindings. You could have got the object Newton options, and then that object has got different members. One is called solution, the other is not. I mean, you could have done in a more standard way, but if you want, you can use structural bindings to get all the information that is inside what a Newton solver returns, the solution, the last residual, the step length, the number of iterations, if it has converged, if it has stagnated. Okay? And now, okay, I repeat with a different, here I'm using the discrete Jacobian instead of using the exact Jacobian. I change the Jacobian, leave everything the same. I just change the Jacobian, and then I use Broiden. So I just change the Jacobian and I use Broiden instead of. You see, there is the little method make Jacobian that allows you to get a different type, different approximate Jacobian. Okay, so this is exact Jacobian. Okay, but these are approximate Jacobian, and you can get it with make Jacobian, and make Jacobian is just here. Is a Jacobian factory. depending on an enumerator. You have the discrete Jacobian, the identity Jacobian, the full Jacobian, but then the full Jacobian you need then to set the function that you have defined yourself, Broiden, and so on. So you have everything here. And you also have